It's a little bit intimidating to be giving the last talk of the workshop, but I'll try to do my best to give it a fitting conclusion. It's really exciting that all of the pieces which we need for our return to the moon are falling into place, seemingly over the past few months. This meeting is an essential component of the journey, and I'm grateful to be here. I think it's something which we're going to remember for a long time to come. Today, I'm going to be presenting an LROC image analysis of Malapert Massif. You should be able to see the recent oblique LROC image of the site, but I guess it's not showing up on the title slide. And I'm advocating this site because I think it balances a lot of the scientific and operational priorities which we're working with here. If you go to the next slide, please. When we're trying to select an Artemis landing site, we really need to balance three different objectives. First and foremost, of course, are the mission's engineering constraints and the safety of our crew. Once we've satisfied that, it's desirable to have permanently showered regions at the landing site because those are important for determining the presence of ice and other volatiles. But volatiles only address one of the 7 objectives of the Artemis 3 SDT report. So we also would like diverse geological targets at the landing site, which we can access. And I think Malapert lies at the intersection of these 3 different priorities, as we're going to see in this talk. Next slide, please. The previous 2 speakers have given a great introduction to the site. It's a pretty impressive topographic feature. So from the floor of nearby Haworth crater to the summit of Malapert, you see about the same elevation change as the height of Mount Everest above sea level on Earth. Next slide. From a geological perspective, this is a really intriguing site because it lies along the rim of the South Polacan Basin. So the mountain and the surrounding massifs likely originated when the SPA impact uplifted material from deep within the lunar crust to form this ring of massifs, which have then been dissected. And Jim had presented the map on the right yesterday, and you see that in his map, Malapert is one of only 3 Artemis sites where we can access landforms that were created by the SPA impact. So by visiting this site, we can potentially learn more about SPA, which has been the primary goal of the lunar science community for the past 3 decadal surveys. Next slide, please. So Malapert region is 25 by 25 kilometers in diameter, but today I'm going to focus on one particular proposed landing site, which was selected because of its proximity to a moderately sized 1 kilometer diameter crater. And that crater has a couple important properties which enhance the scientific return of the site. I'll describe those in a couple minutes. Next slide, please. Once you land, it's a pretty spectacular view in all directions. To the north, you can see the heavily cratered feldspathic highlands. Next slide. To the west, you can see some other massifs forming the rim of the SPA basin. Next. To the south, you can see Shackleton Crater and other large PSRs, which are going to eventually be the site of the Artemis Base Camp. And next. And then to the east, you can see the plateau of what I believe is now called Mons Mercure. So this is a landing site that has grandeur, and I think visiting this place would really capture the public imagination and help spur support for a sustained presence on the moon. Next slide, please. Zeroing in on the landing site itself, for the purposes of this study, I'm assuming that there is a 2-kilometer walk-back radius for the crew. All the targets which I'm going to describe in this presentation are denoted on the map, and in particular, I would just like to note the location of that 1-kilometer diameter crater, which I mentioned earlier, on the northwestern edge of the walk-back radius. Next slide. Well, there was supposed to be an animation showing that box coming in, but if you can see part of it, there's an LROC DTM of the site. And while the flanks of the mountain are relatively steep and probably inaccessible, the linear ridge crest along its summit has pretty benign slopes, in many places less than 5 degrees. So you can land there, and then there are traversable pathways to all of these sites of scientific interest for the crew. And Malapert's summit is also 70% illuminated, So, so that would, by going to a highly illuminated site such as this one, it would allow us to optimize crew training for the unique geology present at one or two sites. And also, it would allow us to deploy a long-lived solar powered instrument package, which would satisfy Objective 5 of the SDT report, allow long-lived observations of the moon and the universe. Next slide, please. This is the 1 kilometer diameter crater, and which I've mentioned a couple of times, and there would be an animation here. This is not present on the slide, but you can see in over 30 different L-rock images, there's an area of about 5 square meters, which is in shadow, and it remains in shadow even with lighting boundary conditions. So this is likely a PSR. It's shaded from the north by the wall of the crater, and from the south by the Malapert Massif ridge crest. Next slide, please. And we can see a second PSR at the southeastern boundary of the walkback radius. It's slightly smaller, and it's located directly on the ridge crest, so most of the floor of that crater is in shadow. Next slide. And the real intriguing thing about these PSRs is that they both appear to be permanently shadowed in L-rock imagery. But if we look at diviner radiometer data, the instrument predicts that there should not be ice in the first PSR, but there should be ice within about a meter of the surface at the second. And so by going to the site, we can test our models for ice stability near the South Pole, which will be important for planning future human exploration in the Artemis Space Camp. Next slide, please. This 1 kilometer diameter crater is also an enticing target because it is surrounded by several clusters of boulders, both on its floor and on its rim. The largest is about 6 meters in diameter, which makes it comparable to house rock on Apollo 16. And these boulders likely are pieces of bedrock from the interior of Malapert Massif, which were exhumed and brought to the surface by this impact. Next slide, please. Is the next slide coming up? These are high-value sampling targets because Malapert lies on the boundary between the two unsampled lunar terrains, the feldspathic highlands and the SPA basin. So these boulders most likely represent ancient feldspathic highlands material, predominantly magnesian anorthosite, which was brought to the surface by the SPA impact. But there could also be SPA impact melt mixed in there if it ponded along the rim of the basin. So by going to the site, we could sample one or both of these terrains and significantly improve our understanding of the moon's composition and history. Next slide, please. And we can see more rock exposures on the floor of this small 30-meter diameter crater. You can see it has a rough surface texture in 2 separate L-rock images, so this most likely is not an artifact of lighting. Next. In terms of both size and morphology, this crater is analogous to Lil West crater, which was visited on Apollo 11. You can see more exposures of boulders on the floor of this crater. Next slide, please. Jim had already talked a little bit about the elephant hide terrain. It's ubiquitous on lunar massifs, including Malapert, and it's hypothesized to be the result of downhill regolith creep. So by using a geotechnics package, we can test that hypothesis. And also, the regolith on Malapert is likely well developed and mature because the feature has been there for 4.2 billion years. So it might preserve a long-term record of solar activity. Next slide, please. The Malapert Ridge crest also faces several large basins near the South Pole, which contain large permanently shadowed regions. So since the mountain is 4.2 billion years old, it would have intercepted ejecta from these craters. So an astronaut with a rake like Jack in the picture at the right might be able to walk along the ridge crest and collect a selection of clasts which were ejected by one or more of these craters that will allow us to not only date the impacts, but place a maximum bound on the age of the ice in their PSRs. So this would allow us to not only improve our understanding of lunar chronology overall, but the South Pole region in particular. Next.
2 minutes.
Thank you. So wrapping up, I think this is a really exciting landing site because it satisfies the scientific objectives and the engineering constraints which we have when we're trying to select a site for Artemis. And I think it's a great site to keep in our toolbox going forward, just to maximize the number of options we have for mission availability.
Great view.
Thank you. Huh?
I said great view.
Oh, thank you. And so thank you for listening, and thank you, Lillian, for flipping through all of those slides. I know it was a lot. A couple days ago, I realized that there are currently fewer living moonwalkers than there are living US presidents. And I'm really honored to be here at the meeting where we're trying to reverse that trend. Looking forward to an exciting future on the moon. Thank you.